Hello. Today we're going to fill out my rotational translational foldable. It shows the connection between translational and rotational. I found that students typically had a lot of trouble with this idea of what rotational was and how it connects to what we've already learned during the year as being translational motion. So what I do is I'm going to start by writing on this side. This will be my translational side, and I like to sketch like that's a glide or a slide across the surface. There's no turning on this object right now. And then what I usually do is I have my students start, as I write definitions, to use this as a review for what is going on. What am I defining as I do these images and definitions? So as you're filling it out, why don't you try and figure out what word we're defining, and then I'll show you how it connects to our next word that will lead us into rotational. So if we start here, the first definition is going to be the length of the path an object takes. All right, and so a lot of times I'll draw a little picture to kind of help them see some more what's going on here. So we're going to do a little representation. So if I have an x1, and we have x2, and we have our change in x. And so hopefully by now your students have guessed, or you have guessed if you're watching this right now, that that is talking about distance or displacement. So over here we need to do some review. So distance is going to be used in variables as d, s, r, x, y, dot, dot, dot. So lots of different variables that can be used for this. And I like to point this out now because we're going to start to see a lot more of these, like s being arc length and r is radius and so forth and so on. The unit, again, this is going to be important for us, is meters. And so you have the unit is meters, which is just m. And then we get to some of our equations. And so hopefully you remember that we had our displacement is the initial plus velocity times time, or you can use the displacement formula or position formula, x naught plus v naught t plus 1/2 at squared. All right, so that is distance. Now, when we talk about a circle and we talk about how is it moving, and we think about the distance that it's gone through, we call that a little bit of a different term. But these are going to be what I like to call an analog. So if you know the one, it's going to be really easy to understand the second one. So our new word is angular position. And so that really makes sense. I just said this is position formula. So down here we have angular position, and that's going to be in terms of theta. And so that kind of makes sense if you think about our circles in the past, that we understand that circles sweep through an angle as they're going around. And so the unit for this is radians. And some of you knew that from pre-cal and some other classes. What's really cool, though, is we're going to start learning analog. So the equation is actually the same. It's just that instead of x, we're going to use theta. So my new equation is theta equals theta naught plus omega t. Or if we go to my other form here, we can have theta is equal to theta naught plus omega naught t plus 1/2, and we're going to have alpha t squared. And you're probably like, now wait, there's a couple other variables there. Now, hopefully you've already seen, and we talked about it in class, that omega is our angular velocity. So you've seen that one before, and this one's a little bit new as well, but you'll notice that it is alpha for rotational. Alpha is my acceleration in rotational, so you'll notice that I have an A there and I have an alpha here. All right, so let's continue on, and we're going to actually do our definition for angular so that you can fill in that part as well, and you can see what is going to happen as we go forward. So and how they're related. So this definition for angular position is the number of radians that the object circular path turns through. All right. And so when we're thinking that way, we're thinking about our circle and that it's going to be, here's my circle, and that we have some sort of angle that it's going through. And there's my theta. And so here you have your R, and like I said, technically out here is the S, so your arc length if you need that. And so we're just sweeping through this place here. All right, so let's go back to the beginning and we'll do another definition and see if you can guess the next definition. Probably can already have a guess, but we'll go here. So the rate at which the object's distance along a path changes. Okay, so the rate at which the object's path changes. So this is going to be velocity, specifically velocity tangential. So again, I'm going to look at this in terms of a circle. And we're going to say that here we're looking at how this V, the V sub t, is moving. All right, so we've opened this up and we'll get our next definition. And so here we have velocity. Like I said, specifically the velocity tangential is the one that's going to connect here. So that's V sub t, and its unit was meters per second, right? And we have some equations again. So we had velocity is V naught plus AT, and or you can use VF squared equals V naught squared plus 2A delta X. And so here again, we're going to have this connection point, and we've already kind of seen it before, but if you don't remember, you should make a guess. What variable is going to be over here? Well, none other than angular velocity, and that is omega W. So the unit here is radians per second. And you'll notice, again, this was radians, now we're at radians per second, we were in meters, now we're in meters per second. All of this is very logical in its progression. And so as we go across, we'll notice that the V is now omega. So like I said, it's just your analog, it's your cross point, what's happening there. If you don't like the word analog, maybe you like the word from mapping, like in algebra class, so where X maps to a Y. So the same sort of thing, you'll notice these equations are identical. And so there you are. We have that, and we have omega final squared is equal to omega naught squared plus 2 alpha delta theta. And there we have angular velocity. So angular velocity is the rate at which the object angular position changes. And so again, we're talking about how quickly does it sweep through that, and it's going to be, again, here's my little circles. And so we're looking at, it went through this theta, and so we're looking at how quickly is that velocity or omega changing as we turn there. All right, so we've done distance and velocity. So next up is, ba-da-bum-bum, I'm going to let you guess, the rate at which the object's speed changes. And again, we're talking about tangential speeds when we're talking about this. Okay, so it's going to be acceleration. And so here again, we have all of our different types. We have the A sub c. You have your acceleration can be positive or negative. So let's say that's positive and this is negative. Maybe my velocity was down like it was in the picture above. And so that's where we're going to have acceleration and a positive there. All right, so hopefully you knew all that. And so we're going to go inside and we'll look at tangential acceleration. So tangential acceleration is A sub t, and we're going to say that the unit again is meters per second squared. And we've had the equation A equals delta V delta t. And obviously any of our other equations that you've already seen with an acceleration can be rearranged, but we're just going to look at this one for right now. And so what happens here is, again, we connect to what we will call, shockingly, angular acceleration. So you're probably seeing a trend there. And like I said before, that is alpha. So alpha, or the fish symbol, is our angular acceleration. So this is our unit. And probably, again, you can make the prediction that this is going to be radians per second squared. And so then my equation, again, is alpha, but now it's delta omega over delta t. So that, by definition, is the rate at which the object's angular speed changes. All right, and so we're looking at how quickly is the angular speed changing. And so again, we're still looking at this idea where we have our theta and we have our omega, but now we can have an alpha that would be positive, or you can have an alpha that is negative. And so you have this process where, again, we're dealing with curvatures instead of straight lines now. All right, so we've done what you probably expected, but there are two more blanks. So what else could I need to define here that we've learned before that will show up in rotational? And so this is usually where my students struggle a little bit, but hopefully you can figure out some of them. So the first one we're going to start with, let's just start doing our definition and see if you can figure it out, is this is the quantity of matter in a body, okay, regardless of its volume or forces acting on it. All right, and so hopefully you figured out already that's mass. All right, so here's my little silly sketch to go with that. We have this little box, and it's going to be my 1 kilogram object. There you go. All right, so that's mass, and you're like, wait, what, mass? Mass doesn't change. Well, mass does have a few different applications that you'll learn throughout your years if you continue to study physics, but mass is a little different. But I'm betting a lot of you actually know this one. What other term do we often associate with mass? And your hint would be it's Newton's first law. So we actually have mass is going to change to become the moment of inertia. And I'll bet a bunch of you were just happy because you figured that one out. So that symbol is I. The unit is kilogram meters squared. And we have a new equation. Mass didn't have an equation for right now, and so you're not used to that, but I has an equation. We have what's called K, the shape constant, times mass times the radius squared. And you'll learn a lot more about that as we go through class. So like I said, K is our shape constant. All right, so this is, and like I said, it ties to how you've learned Newton's first law. It's the resistance of any physical change in the state of motion. All right, and so, like I said before, I tie this to Newton's first law. And then you have a couple of different kind of ones, and you can look these up. There's all sorts of different shapes and different inertias. And so we have I is 2/5 mr squared, and so forth, just based on which ones you're looking at. All right, so we've done inertia. And the last one in this section, there's more to come. So the last one over here is going to be any interaction that, when unopposed, will change the motion of the object. All right, so that, my friends, is force. And so there's lots of different ways we can kind of sketch that. I like to draw like little people and do stuff like this. So here's my little setup. So we have forces, and so if we looked at this, we would draw like our normal diagram. You'd have a normal force, you have an applied force, we have a gravitational force, and there might even be friction, right? But there's our basic idea of forces. And so here he is. And then what we have is force, and you're all like, wait, force? Again, we know force. So force, with our variable F, and the unit is, again, newtons. And again, I know you know a lot of this stuff already. So there's that, newtons. And we know that the sum of my forces is mass times acceleration. All right? And we've even just recently learned, at least in my class, that we can look at force in terms of momentum as well. And so we have the net force is the change in momentum over time. All right, and so you're like, uh-oh. They're bringing in momentum now. That's going to be a problem in a minute. All right, so we have force. And so in angular, and again, I talk to my students here and say, what do you hear of or think of if I think of a force applied through a turn or an angle? And a lot of them can come up with torque. So torque is our analog for force. And so the unit for torque is Newton meter. So it is Nm, but it's not a joule. Okay, so this is not an energy term. And so here what we have is, again, you have your net torque is I alpha, and then we're also going to get net torque, spoiler alert, is delta L over T. And so there is that piece. All right, we're almost done on here, and then we're going to go do with some other pieces. All right, so force that is applied tangent to the circle rotating about a specific point. All right, and so there's, again, we're going to go back to circles. This whole section is about circles right now. And so you have your radius, and so I can apply a force here at the edge, and we can see that relationship with force, and that's ultimately going to cause a torque here. But you can also have other locations, like I can apply a force at a weird location and create other torques as well, and I'm sure we will see that in class. All right, so far we have filled in this whole section, but we also have the back. So now we're going to work here, and I haven't written on this other side yet. I normally write rotational over there, so let me do that really quick. So this is my rotational side, rotational. And again, same sort of imaging, but pointing out that this is when the object rotates, not just translates. All right, so I'm on the back. Make sure I've got the right orientation. So there you go. So translation will be on the right now, and rotation will be on the left so that you can keep your orientation straight up. All right, so before we get into some more information, we do have some connection pieces. Like I was talking earlier, is this is a very analog system, and so there's some really cool connection points. So we're going to draw a couple of these now and look at how this relationship works. And so again, I'm going to draw pictures and draw some equations and show you some connections here. So there's my circle again, and we'll have a radius of r, and we will do theta is going to be A in this case, so there's theta. And then maybe S for arc length, like I said, is going to be right there. All right, and so what's going to happen is we have equations. And so I have that arc length is actually going to equal the radius times theta, just like so. And so, or you can rearrange it obviously, and theta is equal to the arc length over r. There you go. All right, and so you can see really quickly that we have this nice connection between our distance that it's traveled around the edge and our angle relationship. And what's really cool is all of them have this relationship. So we're going to keep going. And so here's my next one. And so again, if there's my r, and this time we're going to be looking at velocity, but you can probably already guess, or you will by the end of these, know this. So there's my vt, and so it's going to translate into omega. All right, and so what's happening here is we get that v is connected to omega through radius. So v equals r times the angular velocity omega, or we can get to omega by taking velocity and dividing by r. And so that's our nice little connection point. So it's how we can get from rotational to translational. So this page is about making those connections and being able to move from one side of my discussion or foldable to the other. So this is my link between them. So now that we've done distance in velocity, obviously what leaves us with acceleration. And so again, we understand that my acceleration can go a couple of different ways. So if we're saying this is my acceleration tangential and that that's my positive, then that means that the alpha will be in this direction here. And we'll continue working on that as well in a little bit. So, I wanted that to be blue. Okay, so at this point we have our A sub t is equal to R alpha, or alpha is equal to A tangential over R. Okay, so we've done the basics, but then I already alluded to momentum, so you know that's got to be in here somewhere. And we also studied recently kinetic energy. So we need to look at this a little bit too. So we know you can call kinetic a couple of different things, but kinetic energy, you can do E sub k, k, ke, dot, dot, dot. You get the idea. And then we had our I was inertia. So I'm defining some things that we're going to see in our equation in a minute. Inertia. And again, we defined that a second ago. So what happens here, and I'm going to just write them over each other, is kinetic energy we have seen as 1/2 mv squared. But in rotational, we've had stuff change, right? So we have k rot is what I call it, k rot. And so we've already seen that that 1/2 will still be there. But m we just redefined. M was inertia. And so in our new system, we have to switch to m is I, so it's off of the inertia. And that v we already just saw was omega. And so now my new equation for momentum, or not momentum, is in kinetic energy is 1/2 I omega squared. Sorry about that. Finally, on this section, we're going to have our momentum piece. That's why I got distracted. So momentum is mass times velocity in its simplistic form. And so again, I can connect to this. And so I showed you a second ago that momentum is going to become L. Mass again is I for inertia, and V is omega. And again, we'll just write over here so you remember that L is angular momentum. Your angular momentum. And so that is unit of kilogram meters squared times radians per second. And we can have the linear relationship we saw up here still holds, and we get that L is P over R, or P is L times R. So all of that still holds for us, and I didn't mark earlier, so the unit for energy is still joules. All right, so the unit was joules for energy, and we can also apply some other pieces in just a minute. All right, so, and we think we're done, right? But we're not. So you're not quite done, because there is, if we fold it inverted, so I'm going to fold it like so, and this is where the students get really surprised. So I folded it together, translational and everything, and in between, right where we just wrote, is one last section to be filled out. And then we will be done. All right, so now we're on the inside back secret flap. And so back here, we have some other pieces. So we've talked about a lot of different things, but we haven't mentioned everything. So now we're going to work on some of our other things. Ha ha ha, because I just said the first word. We're doing work. So work in our translational setup is W equals force times distance perpendicular, and can also be the change in kinetic from our work energy theorem. And its unit, we all know, is joules. All right, so now we're on to our next piece. What is it in rotational? Well, work is still work, but we'll say it's work rotational. All right, and so work rotational is torque through an angle, so tau theta, and its again unit is still joules. We have some equations still. You have theta was equal to d over r. We can have torque is force times r. And so if I use those together, we can get tau theta is force times r times d over r. And so here we can figure out that work was force times distance, and it is now tau theta. And so that's like a little mini proof. Okay, so we can see that these two do actually match up. So there you go. So that is work. All right, I know you're probably getting really tired. This is a lot of information. So now we're on to power. So we've done energy, work, and now power. So power for translational motion was P equals work over time, or force times distance, because we just saw that is work, over time, or distance over time is velocity. So if you haven't seen that before, there it is. And then units, again, for power is watts. Oh, I didn't do my little connection arrow, because these do go together just like our other analogs earlier. Okay. And then power rotational is going to be power is torque times omega. So, or you can have tau theta over t, which is omega over t. So, and that unit is still watts. All right, moving forward to our next piece. So our next one is impulse. So again, I mentioned a second ago momentum. So why should we leave out impulse? So impulse in the translational sense is J. And again, we know that to be F delta T, and technically it's M delta V because of impulse momentum theory. So that's delta P. Oops, sorry about that. And then we have the unit is Newton seconds. All right, so what is it in rotational? So impulse for rotational is going to be delta L. Okay, so that's like the delta P piece, right? Delta L is equal to I delta omega, which is equal to the net torque delta T. And so there you can see it matches up nicely. And again, its unit is kilogram meters squared per second. All right. But we're still not done. We have 2 more blinks. All right, so down here we're actually going to look at graphical relationships. And I've probably just heard a massive groan from my students across the country. So we love graphs. So we need to understand what's happening here. So we have, for example, a momentum versus time graph. So an L delta t or t graph. And so we can have a function. We'll just make that nice and neat. So this will be graph section, and we're specifically doing momentum versus time. All right, and so here what we're seeing is that rise over run. So my rise over the run, right? So this would be delta L and delta T. So the slope is delta L over delta T, and that is net torque. Look at that. So we have angular over T. And again, you can look above to kind of see why that works. That's right up here. So let's do another one. So the next graph would be force versus distance. Force versus distance. And so we saw that one before, that graph. So if I have force and position or distance, then what we have here is the area was work. You're like, but that's not a new one. That's something we've already known. So the question is, what happens when I do its analog? What about torque versus theta? And so, lo and behold, torque versus theta is still work, because it is just an analog of what we've seen before. All right, we are finally done filling in our rotational, translational, foldable. And it might be a little stiff to begin with, so if you'll move it around a little bit, it'll really help. And my students like to bring this every day to class to help them as we work through some more challenging questions. So I hope you've enjoyed this, and I hope that it's helpful. Let me know if you see any mistakes. Thanks.